We all live on Earth, which thankfully is the most Earth-like planet that we know of. Even out of the 5,000 exoplanets that have been discovered around other stars, none of them look like our solar system. And that's probably not because Earth-like planets aren't out there, but because they're really hard to detect. One way that we find exoplanets is by taking the light from a star and splitting it up into all of its colors. And if the star moves, maybe because a planet is pulling on it with its gravity, the spectrum will move too, according to the Doppler effect. But planets are really small compared to their stars. An Earth-sized planet would tug on its sun-like star about this fast. That would make the spectrum move across our camera by 1/10,000th of a pixel. That's 5 atoms in length. So our group at Caltech built the Keck Planet Finder that can measure signals about 3 times that. So we're getting close. But the stars themselves are not static sources of light. Surfaces bubble with convection, and star spots rotate in and out of view. And all this will change the light from the star and make the spectrum appear to move around 10 times more than an Earth-sized planet would. That's a problem. So how do you know how much of that motion is from the star and how much is from the planet that you're trying to discover in the first place? Thankfully, we have one example where the answer is in the back of the book. Our sun is a pretty sun-like star, and we know where all the planets are in the solar system. So if we look at the sun, we can perfectly remove the signals of the planets. And we know where all the sunspots are too, so we can correlate them to any variability that's left over. So I built the solar calibrator, or I call SoCal, on the roof of Keck Observatory, so we can do this measurement on the sun. And we have 40,000 spectra and counting that we can use to develop new methodologies for combating this star spot noise. Of course, our goal is to conduct the galactic census of Earth-like exoplanets. But in order to understand things like how planets form and evolve, we can often learn the most by looking at the most extreme systems. So at nighttime with Keck, I looked at the planet Kelt 18b, a Jupiter-sized planet that orbits its star 10 times closer to its star than Mercury to our sun. Planet formation theory says you can't form giant planets that close to their star, so something's up. When I looked at it with Keck, I saw the planets going around the poles of its star, very unlike the planets in our solar system that neatly orbit the sun's equator. We also saw a second star further out in the system that could have pushed a planet like our own Jupiter from far out, where it's really easy to make giant planets, all the way in to where we see it today. And this process would naturally tilt the orbit as well. So if planets do migrate like this, we might get lucky and catch some in the act of doing so, on long, elongated orbits stretching from where they formed all the way to where they end up. And that looks to be the case in this planet Kepler 1656b, but when I measured its orbit, it's actually aligned with the equator of its star. This completely contradicts the story I just told you of how giant planets migrate. It's funny, a hot Jupiter was the first exoplanet discovered back in 1995, and to this day, we don't have a consensus on how they form. Sometimes when you look for planets and search the universe for answers, first you find more questions, but that's science.